Hello everyone, and welcome to the second lecture on industrial toxicology. Our previous lecture looked at a number of definitions, and there will be some overlap in terms of definitions and explanations in this lecture as well. This lecture will also be looking at some relevant methods of studying in toxicology and experimentation in toxicology, as well as relevant equations. And it also contains various examples of popular known toxins that prevail in various spheres of industry at the moment. Okay, so there will be a bit of overlap, and this lecture does end with aspects of impact on engineering activity, which is essentially self-explanatory. So I'm going to leave that part as a self-study for you, because you can quite easily just read it by yourself. So just to go through the notes. Okay, so we've looked at the definition of toxicology, and that's essentially the adverse effect on chemicals on living organisms, the quantitative effect of chemicals on biological tissue. And interestingly, the opposite of toxicology is pharmacology, which looks at the positive effect of chemicals on living organisms. Okay, in relevance to industry, in our engineering activity and in our various factories, the leading work-related disease is actually lung disease, right? Various types of respiratory problems as well, because your lungs are a major biomode of entry. Okay, so we can typically control what we ingest, and also to another extent we can control what is spilled on our skin. We can try and prevent that. However, it's quite difficult to prevent what we breathe, to try and control what we breathe. And if we are in a room, we of course need to breathe, and so we are at the mercy of whatever air is in that room. And so inevitably in various industries there are various lung related complications. Okay, so common complications are typically associated with industries that work with a lot of fiber. Okay, so paper industries, asbestos, sugar mills. So a lot of industries that work with pulp and paper and fibrous material. Okay, so and the reason why it is so common as well is not only is it dangerous, but it's also, you don't really need to be exposed to it for a number of times. Okay, in certain cases, for example, with asbestos, they used to have an asbestos industry, and even if you are exposed to it once, you can have chronic conditions for the rest of your life. Okay, because quite often the fibers that you breathe into your lungs, it will just never leave your lungs. It will get stuck in your alveoli, and it will continue to affect your lungs. Okay, thereafter there are various other work-related diseases and injuries, musculoskeletal injuries. Okay, so that's typically associated with falls and explosions. Hopefully they're mostly minor. Okay, various types of cancers, dealing with many carcinogens. Okay, especially not really end products. Okay, so many end products are designed to be safe. We want to use safe products. But typically intermediate products are quite often carcinogens. Okay, so cancer is another work-related disease. Okay, then there's your various other lists which you can read as you go along. Okay, so just a recap on some definitions. So acute and chronic toxicity. For acute toxicity, there are various definitions. Some consider acute toxicity to be over a period of at least 7 days, up to 7 days, or even up to 14 days. Some authors consider it to be, literally acute toxicity of less than 24 hours. Okay, so a good example is VCM. You can actually get cancer just even after a single exposure. Okay, then there's chronic toxicity. Exposure to multiple small quantities of a chemical over a long period of time. And it also looks at your condition over a long period of time, even if your exposure is perhaps only once. Okay, so we've looked at the various interaction routes, the various types of interaction between toxins that you can read on your own. And also we've looked at the entry routes for toxicants. Okay, so perhaps another thing that we haven't looked at is the methods of control. Okay, so ingestion, we can have rules on eating, drinking, smoking, and not just what to eat or drink, but actually where you are allowed to eat or drink, and also various cleanliness measures as well to ensure that you don't ingest something that shouldn't be ingested. Okay, and there's also inhalation. The control of that is the use of ventilation, hoods, protection equipment. There's also extractor fans, filters, etc. Okay, for injection, you can, for example, get cut by your skin, and for that you have protective clothing. And also for dermal absorption as well, you're relying on protective clothing. Okay, so just a few points on dermatosis. So this is occupational dermatitis. Okay, so essentially various types of skin conditions. Okay, so allergic reactions to chemicals, plants, wood, tars, chlorinated hydrocarbons are a popular candidate to cause types of skin irritations and disease. Okay, coal tar and petroleum fractions can, at the extreme case, cause skin cancer. Okay, there's also various other initiators of dermatosis, so radiant energy, contact with acids and solvents, various sensitizers as well, such as like fiberglass or even something as simple as sawdust. Okay, it's an irritant and a sensitizer. Okay, so certain examples. So your barium ions used in X-ray examination, they're soluble and toxic. Okay, so they can be absorbed by the skin to a certain extent. Okay, and there's your chromium compounds as well. Okay, which serve as a skin irritant. Mercury is also popular for causing various types of dermatosis. Okay, and its toxic effect is wide-ranging on the entire system, can affect your emotional stability and even muscle control. Okay, then there is lead, which can, not lead itself, but essentially lead compounds can penetrate through the skin and attack your red blood cells. Okay, it can also cause mental and physical retardation of children. Okay, so very serious conditions there. Tin as well is responsible for liver disease in organic compounds. So remember that we do have tin cans, which are quite nice for preserving food in canned food. That's why canned food lasts so long before it actually decomposes. However, don't ever try and cook in tin or heat that tin can up and touch that tin. It wouldn't be a good idea. Some of it can get absorbed, and that can result in liver disease. Okay, then there's of course simpler compounds that you perhaps don't think about. So things like carbon dioxide and nitrogen at very high concentrations, it can be a hazard and it can get through your skin. Also carbon monoxide as well. So what's coming out of your vehicles at very high concentrations, it can go through your skin and attack your red blood cells. Okay, and also hydrogen cyanide. Okay, various complications there as well. Okay, in terms of categorization, what is considered very highly toxic or less toxic? Okay, so this is just a table of, this is just a guide over here. So your LD50 per kg of any organism. So something that's extremely toxic is something that can actually cause adverse effects even if you're exposed to less than 1 milligram per kg. So for a 70 kg adult, if you're exposed to even less than 70 milligrams of this, it will have adverse effects. So that's what's considered extremely toxic. Okay, and then highly toxic, that's 1 to 50 milligrams, moderately toxic, and slightly toxic, etc. It goes on. Okay, and relatively harmless is if you're exposed to something that's greater than 15 grams and it's not causing any effect. So that's essentially considered harmless. Okay, so threshold limit values, these are just some examples. Okay, so that's air concentrations. Just to give you an idea of the amounts and what is considered high or low. Okay, so we've also looked at our various definitions of LD50 and LC50, so I won't waste too much of time on that. You can read through that on your own. Also, developmental toxicity, teratogenicity, genetic toxicity, etc. We've looked at that as well. Moving on to examples of some toxic chemicals. Okay, and issues of toxic chemicals. So in terms of irritants, common irritants include soluble chemicals such as chlorine and even your NOx's. They typically can cause inflammation and other types of irritations upon the body. And irritation is not only a skin irritant, but it can be internal as well. So it can cause inflammation of your muscles, for example. Okay, and then you get dermatitis, which can be caused if you are in contact with various acids, alkalis, solvents, etc. Okay, now sensitizers are different to irritants. They are different in the sense that they essentially produce an allergic response. Okay, and they're highly specific and they may occur within 10 days. Okay, so they can cause inflammation. Chromates, for example, pitch, as well as dyes and coal tar. Then you also have respiratory sensitizers, where over time, at least within 10 days, you can get tightness in your chest, cough, asthma. Okay, so these are typically interpreted as allergic responses. Okay, and then you get asphyxiants, say, such as your nitrogen and CO2. If they're in very high concentrations, they can asphyxiate you. And various anesthetics and narcotics have an effect on your central nervous system. Okay, typically the hazards are associated with hydrocarbons, chlorinated solvents, and ether. So essentially a fossil fuel organic compound industry. Okay, and then you get respiratory fibrogens. Okay, so common sources of hazard are silica and asbestos. Asbestos usage has dropped significantly, so before they used to even make asbestos products, they don't do that anymore at all. However, it is used in very limited amounts, but it is nevertheless a hazard. Okay, so remember, it gets into your lungs, it cuts your alveoli and causes scar tissue. So you have a reduction in your lung elasticity and you end up with breathing problems. Okay, and thereafter, like dust morphology, okay, silicon dioxide, free crystalline silica, they're also fibrogenic. They're fibers. Okay, in terms of what type of fiber is dangerous or not, in terms of the size of dust, anything greater than 50 microns is not going to enter the respiratory system. Well, not usually. Between 10 and 50, it can affect your upper respiratory tract and cause irritation and inflammation. Between 2 and 10 microns, it can get into your lungs and it can get into your trachea, your bronchi, and bronchioles. However, anything smaller than that, and it's going to get right into your alveoli. And at this point, it's not going to come out. Once it gets in, it gets stuck in your lungs for life, and you have deteriorating breathing problems. Okay, and then we have carcinogens. The common ones include asbestos, benzene, VCM, okay, in your polymer industry, hematite in the mining industry, and also various others, so nickel, isopropanol. These are all common carcinogens that we work with in industry. Okay, there are certain chemicals that are probably carcinogenic. Okay, that includes your beryllium, cadmium, carbon tetrachloride. Okay, now the reason why it's saying probably carcinogenic is because it's not really a case of in these industries people are exposed to just beryllium or cadmium. They're exposed to various mixtures containing these compounds. Okay, so these are the likely suspects that are actually causing that carcinogenic effect. Okay, and lastly, you get the issue of mineral oils, which typically have low acute toxicity. They're also not absorbed via the skin. However, over very long-term exposure, you can end up with skin cancer. It's an irritant on the surface of your skin. And if you inhale oil mists, that can result in lung irritation and even pneumonia. Okay, so in terms of mineral oils, your threshold limit value over a time-weighted average of 8 hours, that is actually 5 milligrams per meter cubed. And in terms of just 10 minutes, it shouldn't be more than 10 milligrams per meter cubed. Okay, so those are the common examples that are out there in industry right now. So if you graduate and when you graduate and you get employed in various engineering firms and various industries, you can expect to encounter many of these common toxins or toxicants. Okay, and now on to hygienic standards. We've talked a lot about dosage. Okay, so lethal dosage 50. There's also other terminology such as your lethal dosage ceiling, lethal dosage low, etc. Okay, we've looked at that in the previous lecture. However, we haven't spoken much about exposure times and exposure limits. Okay, so looking at some of the typical exposure values. So this is your threshold limit value exposed over a time-weighted average. And that time-weighted average is typically the length of a typical shift cycle, so an 8-hour work cycle. Okay, so TLV, TWA is the total intake of contaminant over a period of 8 hours. Your short-term exposure limit refers to very acute effects, so exposure to a chemical for at least 10 to 15 minutes. Okay, then you have the threshold limit value C, which stands for ceiling. This is the TLV that shouldn't be exceeded at any time. So regardless of time, there is a certain dosage that you shouldn't be exposed to at any time. Okay, and then there is the maximum exposure limit, which refers to the maximum concentration of airborne substance and exposure by inhalation. Okay, so this is typically relevant for ingestion and dosages. Your maximum exposure limit is relevant for inhalation. Okay, then there are other definitions such as your PEL, permissible exposure limit. And in the UK, there's another term known as the occupational exposure standard. Okay, so this is your concentration of an airborne substance averaged over a reference period. Okay, so these are essentially your hygienic standards. Some shortcomings of these standards: they are typically rated for pure compounds, so the effect of mixtures can be quite uncertain unless you specifically test them yourself. You can investigate the additive or synergistic or antagonistic effect of certain mixtures. Okay, also the effect of extended working hours. Not everyone works an 8-hour day. Some people work a lot longer than that. There's overtime and, of course, the enticement of overtime pay. But what is the effect of extended exposure? Okay, and there's also a certain extent of subjectivity to hygienic standards because it depends on a person's pre-existing medical conditions. Remember that these toxicology studies are typically an average, and it depends on the person as well. So certain people can get an allergic reaction or an adverse effect a lot quicker than others. Okay, there's also changes in the knowledge of toxicology as well. So in terms of this, we have to always continuously keep up with various standards. Okay, so a good example of this is the effect of testing. So remember, we've looked at concepts known as the LD50 and LC50. However, there's the study of that concept has been conducted since 1927. And there are actually new methods of testing now that essentially produce similar results, and also they result in less animal testing as well. Okay, so there's various changes in the way we study and approach toxicology, and that needs to be updated. Okay, so in terms of dealing with our various hazards associated with our toxins, okay, so typical strategies include substitution, trying to find less toxic and less volatile alternatives, or less dusty alternatives, and also minimize inventory. Okay, so having a large inventory might be good for a stable production and production rate. However, if you're working with really dangerous chemicals or compounds, the issue of safety needs to be taken into account, and that actually calls for the minimization of inventory. And also various handling procedures. Okay, so pipelines, and in terms of transferring pressurization or use of vacuum, abundant use of scrubbing and filtration, and incineration of vapors at the stack, as well as various container designs that keep getting upgraded. Okay, and now we're going to look at essentially the method in which toxicology studies occur. Okay, so let me just get up to date with my notes here. Okay, so typical toxicology experiments typically involve some type of animal testing. Okay, now those animals range from your simple fruit flies. They also can include mice, guinea pigs, rabbits. In extreme cases, they also look at studies on cats and dogs, and even apes as well, so primates. In terms of aquatic toxicity, they've also performed studies on fish as well. Okay, so these various animals are actually used to perform toxicology experiments. Okay, so up to 5,000 animals are used to test each chemical. Okay, so just out of interest, so working with, let's say, a whole population of mice or a whole population of rabbits, for example, it takes at least 5,000 of those animals that you need to test the chemical on, in order to actually establish all of the key toxicity concepts and or toxicity values. In terms of the pesticide industry, because pesticides, they're being sprayed on our crops, so studies are actually a lot more stringent, and you can have up to 12,000 animals being used to study a single pesticide. Okay, so typical populations start with 50 rabbits, and the general idea is to expose that population to a fixed concentration or a fixed dosage of a particular chemical. And you would, of course, get a variety of responses. Okay, so not all of the mammals are the same. Okay, in terms of the choice of animals, okay, so typically your mice, your rats or guinea pigs, they typically used for most studies. Rabbits are typically used to look at issues of adverse effects on vision, okay, on your ocular concepts or ocular hazards, okay. And fish is again for aquatic toxicity. Cats and dogs, they perform studies on cats and dogs typically because cats and dogs are typically free roaming. So any industry that has emissions of chemicals into the atmosphere, or even if you're spraying pesticides onto the ground, there's typically free roaming cats and dogs, and you want to study the effect on them. And that is typically why they are also involved in the study as well. Okay, so I understand there are, of course, some sensitivities around animal testing, and there have been many measures to actually strive to reduce the population of animals that actually gets exposed to these chemicals. Okay, so there is, for example, the fixed dose procedure rather than the LD50 procedure, which typically gives you the same relevant results in terms of lethal dosages. However, a lot less number of animals are actually used in those studies. Okay, but looking at the general trend, you start with a population of rabbits, you expose them to a fixed concentration, and you get a variety of responses. And you can categorize those responses as follows. So for any given dosage, you expose the population to that dosage and you record the responses. Okay, so some members of that population will have no adverse health effects. Some might have temporary health effects. Some might have light but permanent adverse health effects. And some might have serious permanent health effects. And some members of that population would die. Okay, now based on that, we can plot a response curve and establish an average response. Okay, so looking at your types of responses from 1 to 5, that's the least, or sorry, the best case scenario and the worst case scenario. So let's say for this particular chemical, okay, just any arbitrary chemical, this is what was achieved. So we look at the number. Okay, so this is a total population of 50, and we're looking at the fractions that had the following responses. Okay, so for this particular arbitrary chemical, only 2 rabbits actually had no conditions at all. Some of them had light and temporary health effects. Some had light but permanent health effects. And some had serious effects, and 1 rabbit died. Now, averaging this out, okay, so you multiply the response by your number of rabbits that experience the response, okay, divided by the total. So that's 149 over 50, and you get an average response of 2.98. Okay, so which means that exposure to that particular dosage would give at least, on average, light permanent adverse health effects. Okay, so the fact that you're like 2.98, it's close to 3, and the fact that it's permanent adverse health effects, never mind it's light, so this is already serious enough. Now we can analyze this in a variety of ways, and remember, this response spectrum is all for a single dosage. Okay, now the reason why so many animals need to be used is because you need to investigate different dosages. Okay, so for different dosages, you perform the same experiments again and again and again on fresh populations, and you get a response. So for dosage 1, we had 2.98, and for higher and higher and higher dosages, you get the following, and we can plot this as well. And this is typically what's used to determine what is your LD50. Okay, so what dosage will actually kill at least 50% of the population. Now there's various ways of handling these values. So typically if you're looking at a big dosage range, this is the type of curve you get. However, for very toxic chemicals, even at low dosages, you end up with an S-shaped curve like this of dose versus average response. And typically the strategy is to try and linearize this curve so that we can use the equation of that curve in computations. Okay, so one strategy is trying to use the log dosage and plot it against average response. Another strategy is to try and convert the percentages into probates. Okay, so we're looking at probability estimates. So if you express your average response in terms of a percentage, and then you look at the probate table, you can transform those percentages into probates or probability estimates. And the benefit of that is that if you plot log of the dosage against your probate, you get a linearized curve. Okay, and you can use this in various computations. Instead of working with dosage and responses or dosage and percentages, you work with the log of the dose against a probate. Okay, so this is the probate equation here, which I won't really get into. Typically the table here is the result of this equation. Okay, so it's trying to essentially convert an S shape into a linearized shape. Okay, so that is for calculating for dosages. For exposure to concentrations in the air, it's fairly similar. Okay, so remember that a probate is a measure of the probability of an effect, and it can be related to percentage of exposures that would lead to an effect. Okay, so remember, as we looked at the table, each probate is indicative of a certain percentage. Okay, so 3.87, for example, is indicative of 13%. Okay, so that's 10 there and 3, that's 13%. So that's what your 3.87 actually represents. Okay, so for example, a probate of 5 corresponds to your LD50 or LC50, depending on the study that you're performing. And you use that to estimate the consequences of toxic exposures, thermal radiation, and overpressure from explosions as well. Okay, so if we have to plot your probate values against percentage, this is what it is. So as you can see, an S-shaped curve. So if you ever have an S-shaped curve, then you can use probate analysis to actually linearize it, because the probate equation is already an S-shaped curve. Okay, so one example. Okay, now this type of analysis can be conducted not only on chemical toxins, but also on various types of studies. So even something like overpressure and its effect on eardrum rupture in humans. So let's say, for example, someone conducted a study of peak overpressure. Okay, so that can affect essentially 1% of human eardrums. If you increase it higher, it can affect 10%, 50%, or 90%. And the question in this example is determine the probate correlation. So we can convert these percentages into probates quite easily there. And we can take the log of these overpressures and plot them, and we can get a linearized curve from which we can get an equation. Okay, now certain authors make use of ln, the natural log. However, most authors just make use of log to the base 10. Okay, so in our computations, we'll look at log to the base 10 in most cases. Okay, and then on to the subject of evaluation. Okay, we can evaluate exposures to volatile materials by monitoring. So let's say if you already have a certain enterprise running, okay, and you can measure the worker exposures to any chemical in the air. Okay, so a direct method is to continuously monitor the air concentration and get continuous concentration data, and from that you can get a time-weighted average using the following integral. However, in most cases, continuous monitoring can be quite expensive, so they typically look at time-dependent or intermittent samples. Okay, so in which case your time-weighted average depends on the following. So that's your concentration over a certain time period. You add it all up and you divide by your total average time, which is 8 hours for an 8-hour day. Okay, now this is for a pure compound. If you have a number of compounds that's present in the atmosphere, for example, and you have various sensors for each compound, then you can perform studies and look at a mixture threshold limit value over a time-weighted average. Okay, and that's calculated as follows. So the summation of concentrations that were discretely measured over the summation of your concentrations over the individual threshold limit values for each pure compound. Okay, so there is an example in the tutorial concerning this, and we'll go through it as we go along as well. Okay, now how is this equation useful to us in terms of making a decision in our day-to-day operations? If we achieve this equation here, well, in terms of a pure case, we can just simply compare our time-weighted average with our threshold limit values, acceptable TLV, TWA, and if it's higher, then it's not acceptable. Something needs to be done about it. If it's lower, then it should be fine. In terms of your mixture, we have individual threshold limit values. If the summation over here exceeds any of those individual limit values, then we have, a problem that needs to be rectified. Or alternatively, if this summation here exceeds the value of 1, if it just exceeds 1, then it means that workers are overexposed. Okay, so an illustrative example, let's say for example, air contains 5 ppm of diethylamine, 20 ppm of cyclohexanol, and 10 ppm of propylene oxide. Okay, and they've given us the individual TLV, TWAs to be 5 ppm, so that's fine in the case of diethylamine. 20 ppm over here, and 10 ppm for propylene oxide. What is the mixture TLV, and has this level been exceeded? Now, in terms of has this level been exceeded, at least one of the levels has been exceeded, so that we can answer quite easily. We can answer that immediately. However, we can also look at studying this equation as well. So looking at your values, we add up the concentrations here at the top, divided by the concentration over the actual TLV, TWA, and we can get an answer. Okay, now that answer there is 5.5 ppm, which is quite nice to know. However, the key here is to try and compare the denominator and see, is this denominator greater than 1? Or alternatively, if we look at the total mixture concentration, 5 plus 20 plus 10, that's 35 ppm. Okay, so your workers are overexposed under such circumstances. Okay, now the remainder of this lecture concerns the impact of engineering activity, which I will leave as a self-study for you, so you can essentially go through these slides. It looks at typical effects of different gas concentrations. Quite interesting to note. Okay, so for oxygen and carbon dioxide, oxygen deficiencies, carbon monoxide concentrations. Okay, so these are various symptoms that occur at various concentrations. Okay, they've also looked at the use of catalytic converters to reduce a vehicle's emissions of harmful gases. So using platinum rhodium catalysts, there are a number of, so this is your catalytic converter in a vehicle. Okay, this is in a petrol vehicle, of course. And if you look at the catalytic converter, it converts your carbon monoxide to much safer carbon dioxide and also oxidizes your unburned hydrocarbons to carbon dioxide and water, and also reduces your NOx's, which can stem from your fuel. You can convert that to oxygen and nitrogen. Okay, so that's just some of the pictures of a converter. Okay, and then various other chemicals as well and their effects. Okay, so reactions to H2S concentrations. Okay, so this is quite prevalent in the fertilizer industry, which is a very large industry. So H2S and SO2 and its effects on the environment. Okay, so that's SO2 effects. Okay, so there have been considerable effort to reduce emissions of harmful gases, as you can see, over the years. Okay, this is the effect of sulfur dioxide, which you can go through as well. Okay, and that is the end of the lecture. Okay, so remember, if you have any questions, please don't hesitate to send me an email. Okay, these lectures are supplemented by the tutorial as well, so please attempt the tutorial. It uses essentially the equations that are based in this lecture, so please try and attempt that tutorial. I will try and upload some solution guidelines for that tutorial as well. So it's tutorial 3 that I'm talking about at the moment. Okay, so that is the end of toxicology. In our next lectures, we'll look at reactive chemicals as well as flammability issues. Okay, so thank you very much.